Okay, well, let's get started. Welcome everyone to the Topos Institute Colloquium. Today, we're very happy to have Christina Vasilakopoulou talking about dual algebraic structures and enrichment. Please, Christina.
Thank you very much, David. It's really a pleasure for me to be here. So today I will give a talk that mostly summarizes or brings together a number of various themes of my research in the past few years, even starting from my PhD. So I think I'm going to give an overview and also talk a little bit about what I'm working on right now. So this is the outline of my talk. We will begin with some background, a few pieces of what's going to be needed later. Then I'm going to give an overview of Sweedler theory, so-called Sweedler theory for monoids and modules. Then we will move on to the many object generalization of this context and constructions in the setting of categories and something called co-categories and their modules and comodules. And finally, we're going to see some further directions where this machinery, this setting can get us to. Okay, let's begin very simple by talking a little bit about algebras and coalgebras and general monoidal categories. So we fix this monoidal category, and a monoid is, of course, an object together with a multiplication and a unit that satisfy these usual diagrams of associativity and unitality. Of course, algebras, monoids are everywhere. We studied them very early in our careers, in our math studies or elsewise. In abelian groups, these are rings. In the context of vector spaces, which is of very interest to us as a base case, they are k-algebras. And even in the category of categories and functors, they are strict monoidal categories, since this multiplication is required to be strictly associative and not pseudo-associative as usual. Now, the dual notion is a comonoid, which of course is an object together with maps going the other direction and satisfying dual diagrams like the ones you can see on the slide. And we can use the Sweedler notation, so-called Sweedler notation, building up to Sweedler's things with the sigma, taking the sum of elements of this form. In the category of categories, where before we had the strict monoidal category, in fact, any category can be viewed as a comonoid with a diagonal and the discarding. And in fact, this is the case in any Cartesian monoidal category, one category whose monoidal product we take to be the usual Cartesian product. And in fact, this is a characterization of Cartesian monoidal categories. If it has well behaved diagonals and augmentations, then we can show that it's a Cartesian monoidal. Okay, but in other settings, which are non-Cartesian, we get this, for example, R coalgebras for a ring, and we have many examples that people know and have used in the past. We have divided power coalgebra, which is the polynomial ring in one indeterminate. And then we have the tensor algebra, which is the free algebra on a vector space with a primitive like co-multiplication. Okay, the group-like algebra, trigonometric algebras, when you have two generators working together like sine and cosine. Anyway, various versions of these things. As I said, well studied and well thought of. So monoids and comonoids in a general monoidal category V, together with appropriate maps that preserve the multiplication and the units, or the co-multiplication and co-units, they form categories. So those categories play an important role, starting on with this theory, the Sweedler theory. If we start putting some extra structure here in V, if we ask for symmetry to exist, or even braiding is good enough for most of what we will be saying today, we can actually say a bit more about these categories, that monoids and comonoids inherit the monoidal product, because you can see here, if I take the tensor product of two monoids and I take a copy of it and I want to reach the end, then the switch is required to change the place of these two variables and then apply multiplication. Furthermore, in what follows, we will require that our monoidal category is monoidal closed. So the tensor functor has the monoidal closed functor as its adjoint. And in that case, which is really, really important, in what follows, we have the convolution structure on the internal home of a comonoid and a monoid. So we're interested in the fact that the home space, if you will, of a comonoid and a monoid becomes an algebra monoid itself, And it's easier to see that if we take the adjunct under the tensor homoadjunction. So beginning with something like this, we can use the co-multiplication of C to duplicate C. Then we use the symmetry or the grading to switch entries here. So then we can apply evaluation twice and then the multiplication of the algebra. And again, in Sweedler notation, we can see this a bit more compactly via this convolution formula, which is again very well known in vector spaces and otherwise. Okay, let's begin with what is called Sweedler theory, not by me, but I really like the name. So there is an underlying idea here, again, very well known, the fact that for any K coalgebra, the linear dual, the home space from C into K, is a K algebraic convolution, as we saw on the previous slide. But this is not the same, this is not the case for algebras. So the linear dual of an algebra is a coalgebra only when it is finite dimensional. So one idea that we can think of as underlying part of a special case of Sweedler theory is to find an operation that fixes this asymmetry, find something that works like a linear dual, but now is a coalgebra and has a nice correspondence that links it to the linear dual of a coalgebra. But Sweedler's idea, which can be found in his book Hopf algebras back in 1969, is the following. So if we start with three plane vector spaces, then of course, due to the tensor homoadjunction, we have this bijective correspondence between these two home spaces. But we can see that on the right, if A, B is an algebra and C is a coalgebra, then this is an algebra. Home CA is an algebra due to convolution. So one could ask, when are those maps, those linear maps from B to home CA, compatible with the multiplication structure of those two things? And the answer to this question, so the thing that corresponds to an algebra map on the right, if I am on the left, is the notion of a measuring map. So a measuring map is a map from C tensor B to A that satisfies those two properties, that if I translate under this isomorphism, under this underlying adjunction, I get precisely the fact that the corresponding map is an algebra map. So this is the answer that was given there. And in fact, it was shown that there's a universal object like this. So for any two fixed algebras, there is a universal measuring coalgebra, meaning it acts like a terminal object of things that have this property. So there is a unique algebra map from any other coalgebra that measures. So the way this was shown in Sweedler's book, that is to construct explicitly a bijection between those two sets of algebra maps and coalgebra maps from C to this new object P for every A and B. And the way this was constructed was algebraically by starting from the home space from A to B, then taking the co-free coalgebra of this. So, okay, now we have a coalgebra, that's a good starting point, and then take a whole sum of sub-coalgebras for which a natural map measures. In any case, we're not interested in these details, but we're interested in the fact that doing this, we obtain this bijection between these two home sets, which is in fact natural. So one way of saying this is that the convolution functor with a fixed variable has an adjoint PA blank. So that's very nice. And the initial goal, the very initial goal back in my PhD was to obtain this result in a more general setting, not just the vector spaces. So a well-suitable framework to do that was that of locally presentable categories. Very briefly, a category is locally presentable. Well, it has all colimits and it has a very nice set of very well-behaved objects that, in fact, generate every other object under filtered colimits. It's filtered colimit dense for a regular cardinal. Again, not getting into details, that's a very nice setting for obtaining a bunch of results having to do with adjoints and things like that. So this was a very nice passage from the category of vector spaces, where everything happened initially for the measuring coalgebras, to other categories of interest like graded vector spaces, differential graded spaces, more general modules, but of course many more locally presentable categories, like every pre-shift category or growth-ending topos or algebras for a Louvier theory. Really rich collection of examples to work with here. In any way, the first result here says that if V is a symmetric monoidal closed category, which is also locally presentable, then in fact, this convolution, induced convolution functor between comonoids and monoids, which is really the restriction of the internal home of my category, has an adjoint, has a parametrized adjoint. Talking about parametrized because we have two variables here. And this is the new functor, the universal measuring coalgebra functor. So this is really what's going on here. We have the existence of this adjunction. And so about the name of this Sweedler theory for monoidal categories, back in 2013, Anel and Joagal wrote this very, very big paper, long paper, talking about, in fact, parts of a special case of this adjunction in the setting of differentially graded vector spaces. So they were interested in formally understanding the bar-cobar construction for algebras, which has to do with an adjunction between pointed differential graded coalgebras and algebras, and in fact can be viewed as a special case of this adjunction I was talking about earlier. But also what's very involved here is not only convolution and the Sweedler home, which is what we saw on the previous slide, but also another adjoint, which is called the Sweedler product. So now we have a triple of adjunctions, basically, a triple of adjoints, I'm sorry. And those adjunctions in this paper, you can see that they're related to other known constructions relating algebras and coalgebras. Jet algebras, the RAM complexes. I'm just saying a few fancy names out for whoever is interested to take a closer look. Okay, in the fully general setting, of course, we won't build a universal measuring coalgebra as a sum of subcoalgebras, but of course we can obtain this via the adjoint functor theorem that basically produced it, and it is the co-end of coalgebras via the set theoretic co-power of this set of monoid maps. So yeah, the idea is that of course we want to understand this a bit better. So of course in an easy setting like the one in set where we have a Cartesian monoidal structure, of course comonoids, as we said earlier, is just all sets. And this is really the set of algebra maps, okay, not very interesting. Another interesting thing that arises here is that if we go back to vector spaces, we do get an answer to this idea zero I mentioned before, because we can now build the finite Sweedler dual, which is P of AK, and now this is a circle or something, and it's a subspace of the linear dual of A. Of those maps, of those linear maps whose kernel contains a cofinite ideal. So now you see the asymmetry is fixed because we have this natural bijection here of coalgebra maps from C to this finite dual of A, and algebra maps from A to the linear dual of C. So that settles that. But also it is good enough, and it is accurate to think of PAB as a space of generalized algebra maps, because all algebra maps from A to B are inside this PAB, and in fact are the elements that have a group-like co-multiplication of this form. So we can think of PAB as a space of generalized algebra maps. Great. So going a bit further on, we obtained this adjunction having to do with the universal measuring coalgebras, but it was even Gavin Raith back in the 70s, a little bit after this measuring coalgebra thing was around, when he suggested that this introduces an enrichment of the category of algebras in coalgebras. And this is the case, and we can obtain this doing the following. So we can observe that this induced convolution functor has some extra structure. It is in fact an action of the monoidal category of comonoids on the category of monoids. And by action, I simply mean a functor that allows us to act from a monoidal category to an ordinary category equipped with this pseudo-associativity and pseudo-unitality, satisfying some usual axioms. Of course, actions of monoidal categories are well thought and studied, but the point here, the point that is of interest to us, is that every parametrized adjoint of an action gives rise to an enrichment of the ordinary category in V. And this goes back to an old result by Gordon and Power, where they actually showed that there is an equivalence between tensored V category. So V category is equipped with tensors, which is a special sort of weighted limit, and actions with an adjoint. So this is a really beautiful result. And it was even obtained in the context of bicategories, of enriching ordinary categories in bicategories. And this is a special case in the setting of monoidal categories. Anyway, to go back to what we're interested in, we have this action that has an adjoint, and we can put all these pieces together, and under the running assumptions on V, we can indeed obtain an enrichment of the category of monoids in the category of comonoids. And the enriching home functor is precisely this P, this universal measuring coalgebra functor. So all this comes together in this context via this enrichment. And before I go a bit further to modules and comodules and imitate what I said earlier, I will make a short stop to the theory of Hopf categories to just say that this enrichment gives us a bit extra stuff that we hadn't thought about this before. So very briefly, if we think about monoids and comonoids in V, one way that they can be interrelated is the concept of a bialgebra. So a bimonoid in V is a monoid and a comonoid whose monoid structure maps are comonoid maps, and vice versa, and equivalently the other way around. So it is a Hopf monoid, it is a Hopf algebra if it also has an antipode. This is all in the classical setting of a monoidal category, but then one can generalize this to the many object setting. So thinking of a monoid as a category, and then we get the concepts of a semi-Hopf and a Hopf category as the many object generalizations of bialgebras and coalgebras. Let me just very briefly talk about semi-Hopf categories, so the generalization of bialgebras. And now we expect something like a multiplication and a co-multiplication and them being compatible in a bialgebra kind of way. And this is precisely what happens, but it looks a bit funny in the sense that we have inserted all these objects. Those objects weren't here before because we were in the one object settings, but now we have all these indices. So for the multiplication, we have maps like that. In fact, these are just enriching maps as we usually know them, but we see that the indices change. That's why I call this a global multiplication. But the co-multiplication is local in the sense that the indices do not change. So this takes the place of the multiplication of the bialgebra. This takes the place of the co-multiplication of the coalgebra, and the axioms they satisfy look like this. One of them looks like this. And this is precisely the bialgebra axiom if I erase all the indices. But if I insert all the indices, I just need to be careful whether I have globally changing indices or fixed indices for the co-multiplication. So really, a bialgebra, a many object bialgebra, is a category which is enriched in the category of comonoids. And to just close off this slide, the previous results saying that monoids is enriched in comonoids gives us straight away that the category of monoids is a semi-Hopf category. Namely, the category of monoids can be viewed as a many object generalization of a bialgebra. It comes equipped with all these maps here using the universal measuring coalgebra functor. Okay, so that was a brief detour. I hope it wasn't too distracting, but it's good to connect different things together when we have the chance. And now off to modules and comodules. So something very, very analogous to what happened with algebras and coalgebras is now going to take place with their modules and comodules respectively. It was Marge Batchelor back in the 1990s that first defined this notion of a universal measuring comodule in the setting of vector spaces and R modules. And the motivation comes from Sweedler, but she actually worked out a bunch of very interesting applications on connections on bundles and loop algebras and things like that on that paper. So if we want to formally understand what's going on here, we're going to sketch this high-level approach that comes. So for a monoid, for an algebra, we have a whole bunch of A modules, which are things that come together with an action from A that are associative and unital. Now for a comonoid dually, we have those comodules that are objects that come with a coaction, which is very nice and well. and we can form categories of A modules and categories of C comodules with the respective maps that preserve actions and coactions. Great. So these are the categories that are around every time we have a general monoidal category. But and these are the maps between them that we see are well behaved with respect, for example, to the action. But what we are interested in here is some sort of global category of modules and comodules. And what I mean by global is that I do not want to restrict specifically to a fixed monoid or a fixed comonoid, and I want to view those objects equally well for every monoid and every comonoid out there. So I can define categories like that. And now the question would be, what are the maps between them? Because now I have a different monoid acting on the one and the other, for example, in the setting of modules. So this is easily fixed by saying, I will ask for a map between those two different base monoids to be a pair of maps. So I will ask for an underlying monoid map to actually allow me to move from A modules to B modules with this tensoring with F. So this is really a fancy way of talking about restriction of scalars, basically, changing the base of a monoid in the presence of a monoid map that allows me to do so. Great. So these are the global categories of modules and comodules. And using very similar machinery to before, I can start building up my way to the existence of this universal measuring comodule functor. And I will do that straight away. So first of all, not thinking about comodules that measure, someone can do that. We will just think in a high level, saying that the internal home also has this property of restricting, in a sense, in the category of comodules and modules. Basically, for every comodule X and every module M, we can show that their linear home, their home space, has the structure of a module, and specifically the algebra that acts on that module is the convolution algebra of C and A, whereas C is the underlying comonoid for X and A, the underlying monoid for N. So again, using machinery involving locally presentable categories and establishing an adjunction, here we say that this convolution functor has an adjoint, which is the universal measuring comodule functor here. And precisely using the fact that convolution continues to be an action of the category of comodules on modules, I can obtain the enrichment of modules in comodules as before. So what have we got so far? We have monoids being enriched in comonoids using this universal measuring coalgebra functor, modules being enriched in comodules using, again, a sort of a similar way of constructing a universal measuring co-module functor. And to finish up the story, of the Sweedler theory for monoids and modules, I would like to bring those two enrichments together in a natural way. So what is the natural way I'm thinking of here is the one that brings the structure of fibration in the picture. And the structure of fibration is not new, is not outside the picture. It was already there, because completely independently to these enrichments we established, for any monoidal category V, we have a fibration of the global category of modules over monoids and an up-fibration of the global category of comodules over comonoids. And in fact, this is an equivalent way, of course, as for every fibration and up-fibration, to view these global categories. So I'm expecting most of the people to know what they are, but let me just spell out the property of a fibration for modules. So this says that whenever I have a monoid map, an algebra map between two algebras, and a module over the target algebra, then there is a universal lifting here. So there is a new object, a new module above A, which is precisely the restriction of scalars that I talked about earlier, that has the property that for every other module map whose underlying monoid map factors through my initial thing, then this needs to factor through the universal lifting here. So yeah, this is very naturally inside all the structure we talked about so far. So the idea here is how to bring all those things together. On the left, I have the fibrations of modules over monoids. On the right, I have the up fibration of comodules over comonoids. And independently of those two things, we established using Sweedler theory we established an enrichment between the base categories and the total categories. And now the question was how to formalize this. And the answer is, let's introduce a new structure, that of an enriched fibration. And I haven't written the definition here, but basically what it boils down to is a natural thing, I'm hoping people will agree, of having those enrichments around and having the enriching home objects here to be above the enriching home objects down here, using the fibrations and the Hopf fibration. And moreover, for the composition and unit, the enriching composition and unit of the above, the total categories being mapped down by these functors, the composition and the units of the bottom. And in fact, because we wanted to actually formalize this really, not just to work for this example, but to be formally coherent, there is a result like for ordinary enrichment that starts from actions. So we can define what it means for a fibration, for a monoidal fibration to act on a different fibration and to ask for this action, this fibered action, to have a general fibered adjoint. And that situation, or the existence of an adjoint on the context of fibrations, gives us this enrichment on the level of fibrations. Okay, a lot of using the same words over and over again, but yeah, there is a well-defined framework that gives rise to this definition of an enriched fibration right here. Great, let's take a deep breath. This is the end of the Sweedler theory, together with enriching fibrations here on the level of algebras and coalgebras. Let me check the time, we're doing great. We are very ready, I hope, to go on to the next level. Okay, algebras enriched in coalgebras, modules enriched in comodules, a bunch of fibrations and not fibrations flying around. And now we would like to move to the many object settings, similarly to how I briefly mentioned before about Hopf categories. So I'm thinking that a V category with one object is a monoid inside the monoidal category V. So the passage will precisely be that, moving from monoids to categories, pathing up our monoid with many objects and view the home objects basically as being the monoids from before, when we restrict to the one object case. Okay, so monoids become categories, which is well known, and comonoids become co-categories. Of course, as we all know, generalizing from one object to many objects is not a well-defined problem. It doesn't have a unique answer, but I will give the answer that actually allows us to generalize the whole Sweedler theory to the level of categories. So what is the concept of a co-category? So we need to add a bit more extra stuff, structure on our V. We ask for co-products to exist and be preserved by the tensor products. And a V co-category has a certain class or set of objects and home objects in V. And now we have those co-composition arrows that now land on the sum on the right. And here we have these co-unit maps that are only for fixed X. So let me very briefly say, I will explain why this was the chosen many object generalization of comonoids, but let me very briefly say that Hopf categories, which already existed and are just categories enriched in V-Hopf, so this sum really goes away here, are not as convenient formally because for one thing, V-Hopf is not usually as well equipped as V. So if V is, for example, locally presentable, V-Hopf is not. But also, one of our main reasons to do that is because we want to view categories as monads somewhere and co-categories as co-monads somewhere to get the full generalization. And this is the way of doing so, and as follows. So exactly, V categories are monads and V co-categories are co-monads in a specific bi-category of V matrices. So what are V matrices? You may have seen them before. The objects are sets and maps are families indexed by the two sets that act as the domain and codomain. And the reason this structure was called matrices is that the composition reminds us of composition of matrices like this. So we have a Y running through all possibilities here, taking the sum of this thing. Okay, so we have monads in here and comonads in here being the objects of interest. And in fact, one can go on and try and push Sweedler theory to the level of the bicategory of V matrices. So it is the case that VCocat, like comonoids before, now VCocat has all the good properties that allow us to have universal measuring co-categories precisely the same way as before. So we start from a functor here that is convolution in our setting. I will give a definition in a second. And because of local presentability and co-limits and co-completeness of functors and things like that, we obtain this functor that takes as entries two V categories, and gives us a V co-category. So this is the generalization of the universal measuring coalgebra functor from Sweedler. Okay, and just to convince you, so what is this functor that I said looks like convolution? Well, on the level of objects, if I take objects of C and objects of A, then the resulting category has as objects the functions from C to A, which is very good, the power set of the objects. And now the home object is a bit more complicated, but is really just the product of all the home sets here one can build using those F and Gs. Okay, so this is morally the right thing to do. In a couple of slides, it will become the only option. Great. So using again the actions and all the things we said earlier, we can show that we do get an enrichment of V categories in V co-categories. And that's very nice. Those results are a bit technical when writing them down, because we have all these matrices and all these categories we need to make sure that behave in the right way. But while working with those things, it becomes sort of clear at some point that we shouldn't be doing this job for categories and co-categories in specific. We should be doing this job, this work, all this work for more general structures, since we already got that categories are monads somewhere and co-categories are co-monads in that same place. However, the right level of generality, according to me, is not that of bicategories, rather is that of double categories. And the reason for that is that double categories actually have this other sort of arrows that it gives us the opportunity of really viewing categories and co-categories, for example, as monad and monad maps and co-monad maps in there. So let me elaborate. And now that's the reason why we leave all these categories and co-categories behind and just say we want to do Sweedler theory for double categories. That's really what's going on here. So going from monoidal to double categories, let me just say that everything will happen inside the double category of matrices, but of course we do not want to restrict to that. We want to take this framework and use it in every double category of interest to us. Let me very briefly and also take a moment to gather our thoughts together. Let me just say very briefly what a double category is. So a double category consists of an object category where we have 0 cells and vertical 1 cells, and those compose associatively as usual. In many cases and in many other authors, you will see that vertical and horizontal cells have different there are different conventions for them. We choose the ones where the vertical are the strict. And then it has an arrow category whose objects are cells like this, horizontal with a tick in the middle, and 2 morphisms are squares, where the boundaries are vertical, the left and right boundaries are vertical, and the top and bottom are horizontal. Then we have a number of structure maps, the identity structure map, source and target, and composition, and of course, a number of coherent isomorphisms that makes them all work together nicely. Of course, there is a direct passage from double categories to bicategories by considering those 2 morphisms whose boundaries on the left and the right are identities. And then we go completely back to the setting of bicategories. So it is a nice place to work. And if anyone feels the need to, they can pop to the bicategory side and continue working there. Great. So for the double category of V matrices, the object category is that of sets. So we just have sets as objects, and vertical arrows here are just functions, the easiest way of going between 2 sets. And the horizontal bicategory is the bicategory of matrices I talked about earlier. Okay, so that's where everything works in our setting. And now we're off to defining what a monad is in a double category. And if you look very carefully here, it is an object with multiplication and unit of this form. And because the boundaries on the left and the right are equalities, really a monad in a double category is a monad in the horizontal bicategory. So there's no difference there, which is okay, but the real difference is in the maps. The maps of monads and the maps of comonads in double categories become richer because they allow vertical arrows, functions to move between sets. And in fact, it can be seen that that's the right framework to work, for example, for categories and co-categories, because the functors and the co-functors, so the right notion of a map between categories and the right notion of a map between co-categories is really equivalent, is the same as the map between monads and comonads in the double category. And that's not the case for the bicategory of matrices. So maps of bicategories, of monads in bicategories, which is very well established and well defined, do not capture completely the maps between categories. In fact, they are more general than what we need. Okay, very good. So that's where we're going to work. And we will require some extra structure on the double category D for Sweedler theory to arise. As before, we're going to start putting things on top of it. I will just say the names and discuss them very briefly. I'm not going to give now definitions of all those things. The fibrancy condition is very well established and used widely, is a way of turning vertical one cells to horizontal ones by providing a companion and a conjoint together with structural cells, and essentially allows us to move all the vertical structure horizontally. In the setting of matrices, we have that every function gives two matrices going from X to Y and from Y to X with this definition right here. Okay, so that this is a fibrant double category, the double category of matrices. Now, of course, we will need a monoidal structure in our double category. And again, monoidal double categories are everywhere. This is a large class of examples and reasons why people started using double categories more and more. And the definition is very natural. But for us here, just say that D0 and D1, that the category of objects and the category of arrows is monoidal in a compatible way. It's very nice where in double categories, you can formalize, you can say that the structure on this double category is a structure on D0 and D1, because it's much easier to think in terms of two ordinary categories rather than for a bicategory. So for matrices, of course, on the level of objects, which are just sets, the monoidal product, the tensor product, is the Cartesian product of sets. And if I want to talk about the monoidal product of horizontal one of matrices, this is the pointwise monoidal product. So this is the one we're using for V matrices. Now, two extra conditions which are new. The one is called locally closed monoidal double categories. Following the pattern of the monoidal double categories and other structures of double categories, we require for D0 and D1 to be closed as ordinary categories, again in a compatible way. Surprisingly, this definition didn't exist. There was no definition of a closed monoidal double category, although there was a mention of it in a paper by Grandis and Paré, where they discussed adjoints for double functors. But in fact, that definition over there, which was just a brief discussion, did not result in both these categories being closed. So it wasn't good for our purposes. We had to redefine this, I think, in a natural way, in a way that someone would come up to if they really wanted to make this work. I should say that this part of the work I'm talking about is in an ongoing project and in a paper I'm writing with my collaborator, Vasilakopoulou. And this, okay, and for matrices again, let us ground this down. For two different sets, of course, we would expect for the closed structure to be that of a power set, but now this H between matrices is what I defined before. And I said at the time, this is a bit ad hoc in the sense we define the by hand or because we think it's a good idea. And then it turns out to have the things that we wanted to have. But here it really is a locally closed monoidal structure in the double category. So it's not ad hoc anymore. It's the right thing to do. Okay. And the last condition we will need for the double categories to work. And of course, you see how this imitates what's going on in monoidal categories, but monoidal categories are very well equipped with these things, whereas double categories and the concept of a locally presentable double category certainly does not exist in the literature. And this is still, I mean, we have a working definition, but we're still trying to find the the most natural one, in the sense that there are certain concepts of, for example, locally complete bicategories or locally co-complete bicategories. Also for locally presentable bicategories a little bit, there are a few references there, but there's not really, one work done for local presentability in bicategories either, because that would help us, motivate us towards the right direction. So for the moment, again, I'm not giving the full definition. We ask again that D0 and D1 are locally presentable. We ask on co-continuity conditions on the composition functor, and also for the structure and target functors to be continuous right adjoints at the moment. Okay, so with these 4 bullets here of asking of D being fibrant, being monoidal, being locally closed, and being locally presentable, then we can actually say something about Sweedler theory for double categories, which is our current goal. So I hope you see the pattern by now. Even if you just see letters here around, we can show that for a D, a double category with the pieces of structure I mentioned before, and the categories of monads and comonads in this D, there is a parameterized adjunction of this sort. Again, this is supposed to look a lot like the very initial Sweedler's, measuring coalgebra and things. And similarly, the category of monads is enriched in the category of comonads. So at the very end of the day, if you have to keep one thing for the top, it is the case that in a very nicely behaved monoidal double category, like V matrices, but not only, we can enrich the category of monads in the category of comonads. And this really is a direct generalization of Sweedler theory for algebras. Let me just close this slide by saying that, again, we can define modules. Again, we can define comodules. I'm not going to give you all these definitions. And indeed, we can obtain an enrichment of the fibration on the left to the monoidal of fibration on the right. And of course, to not lose the forest behind the tree, a category D, a double category D with a single object and a vertical one cell has the same amount of data as a monoidal category. So we can, in fact, directly obtain everything for monoidal category straight away in this uber generalization of Sweedler theory. Okay, so let me close off by talking a little bit about some further directions of where this framework can take us, because it's okay. Somebody would say it's nice to generalize things, and it's good that we got this this generalization for categories and co-categories. And in fact, co-categories themselves were independently discovered by some people working in A-infinity categories. So I was happy about that too. So those objects are good on their own right, but then why bother just going all the way up to the top of a double category? Okay, we are in a general double category D. We have something that can be called, hopefully with a reason, I hope I convinced you, Sweedler theory. And now the idea is to employ this directly on the setting of other double categories, or even maybe there's the need to extend the theory a little bit to go to other contexts. And let me say what I mean. Okay, in matrices, if we have D being V matrices, then we have the universal measurement co-categories, as I said before. Now, what I'm interested in currently is the double category of symmetric sequences. And the hope is that the machinery developed for D, for a general D, will give us something to be called universal measuring cooperads. So in symmetric sequences, it is very well known that monads therein are operads, okay? And the idea is to view this sort of thing happening to actually provide an enrichment of operads and cooperads just like this, without having to work through all the details of operads and cooperads, but say this works for every monoidal category, double category, such and such, then this will give me the result straight away. So let me very briefly show you how matrices and sequences are very closely related, but not the same, and sequences are really different and more involved, harder. So the objects and the vertical one cells in the double category of sequences and matrices are exactly the same, but for the horizontal one cells, before we had functors like this, but because these are sets, being a functor doesn't say much. It just gives us pairs of objects in V indexed by these two sets. But now symmetries, in fact, have a free symmetric monoidal category on the on the domain. So this is now really a functor, and this the horizontal one cells are much more involved already. And the horizontal composition is really more involved, and it's a slice sort of thing. It has nothing, I mean, it's not as easy to state as the matrix composition one. In two cells, also, here we just had mappings like this, but here we will have tuples of objects in X and then the image of the tuples in X, because we take the free symmetric category there. Let me just say that when I said before that we're going to maybe need to extend the theory, that there is something very interesting happening with sequences. And this is, in fact, in a very recent paper we put out on the archive with Nicola Gambino and Richard Gardner. So the double category of symmetric sequences, it's a very nice double category, but it is not monoidal double. In fact, because it does not have the strict it doesn't have an isomorphism comparison between taking the horizontal composition of two tensors or the tensoring of two compositions. There is no isomorphism there, rather there's just an arrow. So what the symmetric sequences have as a double category is the structure of what we call an oplex monoidal double category. So then, of course, the machinery is not going to work exactly the same way, but with preliminary investigations, it shows that, I don't think it's by accident, that this oplex direction of the tensor product is in fact good enough for Sweedler theory to be developed. It is good enough for those adjunctions to exist and for this enrichment to arise. So by extending, this is what I mean. I really would like to see what's going on with oplex monoidal double categories, which is a new thing, but it's a very important one, thinking that sequences there have this and are not monoidal double categories. So, and let me just close off by saying that the very far-reaching goal of this whole project is to say things about this as the bar construction, the bar construction for algebras, also as was clarified by Anel and Joyal formally using the universal measuring coalgebra structure, then I would like to understand a bit better the bar construction and maybe the operatic causal duality now for operads and co-operads using those adjoint functors and understanding a bit better what's going on there. Okay, that was all. Thank you very much for your attention and for your patience.
Thank you, Christina. So we have time for questions. People can raise their hand in the chat thing, or just unmute and speak. I had a question for a not locally presentable category. What do I need, or what sort of adjoint?
So local presentability is definitely not necessary, it's sufficient. So because we were always focusing more on the concept of on the setting of algebras, of our algebras, I mean for a ring, we haven't really thought about this, but really what's important, I mean, what is used from locally presentable categories to get this universal measuring coalgebra is an easy way of saying that a functor emanating from coalgebras has an adjoint. So this functor from coalgebras, the convolution, is co-continuous. I mean, you have the rest of an adjoint functor theorem. So then one would need to probably pick an adjoint functor theorem and see what other conditions they need on comonoids in a non-locally presentable category and see whether they can obtain them there. So it's definitely doable. I mean, there's definitely a result there. And local presentability just gives us very easy existence of an adjoint to the convolution. That's all.
Cool.
Mm-hmm.
And was it for, you said coalgebras and algebras, but somehow I thought it would also, you were saying it for comonoids and monoids.
Yes, I very often, some people call monoids algebras anyway. So maybe I should stop doing that. But the algebras feel a bit more, we feel more close to them. They're less scary than, and coalgebras a bit more than comonoid. Okay. No, whenever I say algebra and coalgebra, I mean monoid and comonoid in a monoidal category B.
Oh, good. Okay. I didn't realize that. Thanks. Other questions? By the way, I think I have a, what do you call it? An oplax monoidal double category also.
You do? Can I guess?
Yeah.
Is it poly?
It's the comonoids in poly.
Okay.
Comod poly.
That's great. You have to tell me more about this. Really, it's an oplax monoidal thing.
Yep. I think it's oplax monoidal. It's not strong. It's not monoidal in the right way. It's
not strong. Okay.
It's either the one you have or lax, but I think it was oplax.
I would expect it to be, I would be surprising to be lax for some reason that I cannot explain. Okay, I would definitely like to hear more about this, to add more examples to why we would care to do that.
Cool.
Yeah, thanks. Nice.
Well, if there are no other questions, why don't we'll all thank you, but I'll thank you again, Christina.
Thank you very much for having me.
Yeah.
Thank you.
Sometimes when we stop the recording, some people stick around a little later.
They do?
And, if you wanted, if